In this video, I want to talk about the timing of sequential logic circuits. So if you remember from before, we said that the flip-flop samples the D input or the data input at the clock edge. So this is true for all the D flip-flops that we have seen before. So because that is the case, the data input or D must be stable when we are sampling it. So this is similar to when you're capturing a photograph. When you're capturing a photograph, both your camera and the subject needs to be stable or stationary. Otherwise, you end up with a blurry image. So while we don't have this visual representation of a blurry data, what we have is the concept of metastability. As a result of the data input not being stable enough when we are sampling it. So metastability is a state in which you are not sure whether the data that you stored is 0 or 1. I will talk about it more in a later video. So based on these, based on the fact that we need the data to be stable, we can come up with several definitions or several constraints. The first constraint or definition is with the setup time. We show it with T setup, and it is considered as the time before the clock edge at which the data must be stable. So if we have this clock and we know that the D flip-flop is sampling this clock at the edge of the clock. So depending on the design of the flip-flop, it can be the rising edge or the falling edge, but an edge nonetheless. So since we want the data to be stored properly, at least for T setup time, the data should be stable before the clock edge. So the second thing that we need to consider is the hold time. Hold time is the amount of time after the clock edge for which the data needs to be stable. So not only the data needs to be stable for T setup time before the clock edge, but also it needs to be stable for T hold time after the clock edge too. So it needs to be stable during this time. So this is what is called as the aperture time. So aperture time, or TA, is the time around the clock edge for which data needs to be stable. So you can easily drive this equation that the aperture time is the summation of the setup time and the hold time. So that was for stability of the input of a flip-flop. What about the delay that we may have for the output of the flip-flop? You remember from before, for the combinational logic circuit, what we had was that we said for an ideal circuit, when we change the inputs to the combinational logic circuit, the change at the output happens instantaneously. But in real life, depending on all different types of conditions, when we change some input, it may take some time for that change to be reflected at the output. That is why we have delays in logic circuits. But we said the amount of delay is not fixed for any combinational logic circuit. It depends on how many gates a signal has to go through to get from the input to the output. It depends on whether the circuit is kept in a cold place or in a hot place, right? And so many other conditions that can affect the delay of the combinational logic circuit. So a similar thing can happen for the sequential logic circuits too. So similar to a combinational logic circuit, here we define a propagation delay and a contamination delay again. The difference here is that for the combinational logic circuit, we had some inputs that were changing, and that change would be reflected at the output. But for the sequential logic circuit, if we assume that the data satisfies the setup time and the hold time at the input of the register, the change in the output happens as a result of the clock edge, right? Because whenever we have a clock edge, that basically causes the output of the flip-flop to either go to 0 or go to 1. Because of that, we define the propagation and contamination delays as the result of the clock edge that is reflected in the output. So for the propagation delay, we defined it as TPCQ. P is for propagation, C is for the clock edge, and Q is for the output. So this is basically the propagation delay from the clock edge to the output Q of the flip-flop. This is defined as the time after clock edge that the output Q is guaranteed to be stable. So that is the maximum amount of delay from the clock edge to the change in the output. For the contamination delay, we define it as TCCQ. Again, this is time for the contamination delay from the clock edge to the output Q. And this is defined as the time after clock edge that Q might be unstable. So during this period, the output Q might be unstable. So if you look closely, the amount of delay for the output for which Q is stable can vary between these two limits, right? So it's definitely larger than TCCQ and smaller than TPCQ. So now that we have these constraints, we can talk about the dynamic discipline for the sequential logic circuits. So synchronous sequential logic circuits inputs must be stable during aperture time, and also that means that at least for T setup before the clock edge and at least until T hold after the clock edge. So this is a repetition of what I said in a previous slide. But let's just see what are the implications for these constraints. So for this, we assume that we have a register or flip-flop here. We call it R1. We have a combinational logic circuit in between that does some calculations for us. And then we have this second register that basically stores the result of this calculation that is done in the combinational logic circuit. So similar to when we were using simple gates, we said that the timing constraint or the amount of delays for the gates are fixed. A similar thing is true for here too. So we have these registers and we know what are their contamination delays and the propagation delays and also the setup time and the hold time. So these are the things that we cannot change. But what we can change is basically the design of this combinational logic circuit that does some calculations for us. So if we have a clock signal that looks like this, we define TC as the period of the clock. Basically, the time difference between the rising edge of the clock and the next rising edge of the clock. So this is called as TC. We have this first gray arrow that shows the contamination delay from the clock to the output, Q1. So this is TCCQ. We have this first blue array that is TPCQ, the propagation delay from the clock to the output of R1, which is Q1. And one thing that I should note is that this clock and this clock, they are the same clocks. So these two registers get exactly the same clock. The second gray arrow is as a result of the contamination delay in the combinational logic circuit. And the second blue arrow is as a result of propagation delay, again, in the combinational logic circuit. So now that we have this, let's just go over the setup time constraint and also the hold time constraint for our circuit. So the setup time constraint for register R2, for the input of register R2, which is D2, depends on the maximum delay from register R1 through combinational logic circuit through R2. So we need to calculate the maximum amount of delay that can happen as a result of R1 and combinational logic circuit that we have between R1 and R2. So to model that, we consider the figure in the previous slide, but we only consider the blue arrows. First, we have the propagation delay, TPCQ for R1. Then we have the propagation delay for this combinational logic circuit. So assuming that we have TC as a result of, we have TC as the period of this clock signal. For this circuit to work properly, we need to have at least T setup time for the input of R2, right? So that was the constraint for the flip-flop, for the input of the flip-flop. So that means that TC, the period of the clock, needs to be larger than the sum of TPCQ, TPD, which is the propagation delay of the combinational logic circuit, and finally T setup. So if this condition is satisfied, the setup time constraint for R2 is satisfied. Because no matter how big TPCQ or TPD are, the sum of these three values is always smaller than TC. So that means that we have at the minimum T setup time for the data at the input of R2 to be stable. So since we don't have any control, we usually don't have any control on the propagation delay, contamination delay, setup time and hold time of registers, similar to what we didn't have control over for the basic gates. What we have control over is in the design of this combinational logic circuit. So because of that, I can rearrange this equation to see what is the inequality for TPD, or the maximum amount of delay that this combinational logic circuit can introduce. So if I rearrange this equation, I have TPD equals TC minus TPCQ plus T setup. So as long as TPD, or the propagation delay of this combinational logic circuit, is smaller than TC minus the sum of TPCQ and T setup, the setup constraint for the input of register R2 is satisfied. So the sum of TPCQ and T setup is usually called as the sequencing overhead. Basically the sum of propagation delay from the clock edge to the Q output of R1 plus the setup time of the input of R2. So this is the setup time constraint for the input of R2. What about the hold time constraint? For the hold time constraint, this depends on the minimum delay from register R1 through the combinational logic circuit to R2. So the input to register R2 must be stable for at least T hold time after the clock edge. So if we have again this clock edge, we have the first arrow that shows the contamination delay from the clock edge to the output Q1 for R1. So this delay is the TCCQ. Then we have the minimum amount of delay from the input of this combinational logic circuit to its output. So this is the TCD, the contamination delay for this combinational logic circuit. So for the hold time constraint to be satisfied, this hold time needs to be smaller than sum of CCQ and CD, or the T of CCQ and T of CD. So we have T of CCQ plus T of CD. Again, the hold time for the input of register R2 needs to be smaller than the contamination delay of R1 plus the contamination delay of this combinational logic circuit. Again, since we don't have any control on the setup time, hold time, propagation delay, and contamination delay of registers and flip-flops, and only we have control over the design of this combinational logic circuit, I can rearrange this equation to find an upper limit for TCD. So TCD to find a lower limit for TCD. So TCD should be greater than T hold time minus TCCQ. So based on this equation, we found an equality for the maximum propagation delay for the combinational logic circuit, and also we found a minimum value for the contamination delay of this combinational logic circuit. So now, based on these constraints that we found for the contamination delay and the propagation delay of the sequential or the combinational logic circuit that we have between these two registers, let us go over one example. So in this example, as you can see here, we have 4 D flip-flops here on the left side. So this is R1, and then here we have 2 flip-flops that create R2 for us, and in between we have these 3 gates that create the combinational logic circuit that we had in the generic figure. So this is the combinational logic circuit. So for this example, we have some timing characteristics for the flip-flops and also for the individual gates. So the contamination delay for the flip-flops is 30 picoseconds. The propagation delay for the flip-flops is 50 picoseconds. The setup time is 60 picoseconds and the hold time is 70 picoseconds. So pico is basically 10 to the negative 12 seconds. So very small value. As for the individual gates that we have, we have the propagation delay to be 35 picoseconds and the contamination delay for each one of these gates to be 25 picoseconds. So now let's just see if this circuit satisfies the setup time and the hold time constraint for register R2. First, we need to find the propagation delay and the contamination delay of the combinational logic circuit. If you remember from before, the propagation delay was basically the delay associated with the longest path of the circuit. So since this circuit has 3 gates and we said that the propagation delay for all of these individual gates is the same, the propagation delay for this circuit, which you can say is from, let's say, this input goes through the first gate, goes through the second gate, goes through the third gate until it creates output y prime. It's going to be 3 multiplied by the propagation delay of an individual gate. So the propagation delay of this combinational logic circuit is 105 picoseconds. Let's just see what is the contamination delay for this circuit. Contamination delay was the minimum amount of delay for a combinational logic circuit. So the minimum amount of delay is for this input when it basically goes through only one gate and will be used to create y prime. So we have only 1 multiplied by 25 or 25 picoseconds. So these are the propagation delay and the contamination delay of the combinational logic circuit. Now let's just go over the setup time constraint and also the hold time constraint. For the setup time constraint, we know that TC needs to be larger than TPQ, TPCQ, plus TPD, plus T setup. So TPCQ is 50, TPD is 105, and T setup is 60. So if I add all of these together, I have 215 picosecond as the minimum amount for the period of the clock that we use for this circuit. So for this minimum, the frequency is going to be 1 over Tc, or somewhere in the order of 4 point something gigahertz approximately. You can calculate the exact amount yourself. So this circuit can work with a clock signal that has a frequency of 4 point something gigahertz. If you remember, giga is 10 to the power 9. So this clock signal can switch between 0 and 1 more than 4 billion times per second. So as for the setup time, it seems that we don't have any problem. But now, what about the hold time? Let's just see if this inequality is satisfied. So TCCQ, we have 30. TCD, we have 25. And this needs to be greater than the hold time that we require for the input of R2. So 70 picosecond. So 30 plus 25 is 55. But 55 is not greater than 70. So that means that the hold time is not satisfied for this circuit. So now we need to make some minor modifications So the hold time is also satisfied. The modifications are very simple if we introduce these two additional buffers in the shortest path of our combinational logic circuit. We make sure that the hold time constraint is also satisfied. So let's just do the calculations one more time. We have TPD to again be 3 multiplied by 35 picoseconds because the longest path didn't change. So we have 105 picoseconds. For TCD, now we have the minimum size of the path is 2 gates. So either this one or this one. So that means that TCD is now 2 multiplied by 25, which is 50 picoseconds. As for the setup time, nothing has changed. So we have TPCQ plus TPD plus T setup, which if I add all of these values, we get again 215 picoseconds. Which translates to 4.65 gigahertz for the clock. As for the hold time now, we have TCCQ to now be 30 plus TCD, which is now 50, which the summation of these two, 30 plus 50, is now greater than 70. So that means that this circuit satisfies the hold time constraint now. So of course, more and more advanced techniques are out of this scope of this course. But you just saw how by simple modifications you can make the circuit work. So not only satisfy the setup time, but also it satisfies the hold time as well.